Namaskar and welcome to this lecture 31 in the course on hydration, porosity and strength of cementitious materials, where we will discuss paste to concrete transition. Most of the discussion so far in this course has been focused on cement paste, which is a mixture of cement and water. We must remember that paste is the only reactive part of a concrete which also has fine and coarse aggregates, and these aggregates act as inert fillers. They provide the volume and the paste provides the matrix. We've also discussed the constitution of the paste in terms of cement being partly replaced by mineral admixtures, and the details of the hydration process, including formation and properties of hydration products, the heat of hydration involved, the hydration reactions, the kinetics of hydration, the mechanism of hydration reactions, the components of the cement in terms of the tricalcium silicate and the tricalcium aluminates, and in terms of the constituents of cement like C3A, C2S, C3S and so on, and of course also the use of chemical admixtures to alter the hydration products, and also the use of chemical admixtures to alter the hydration process and the products. We could use accelerators, retarders, air entrainers, plasticizers and so on. What we need to do today is to review a bit of what has been covered and try to transition our understanding to concrete and its properties in light of what we have already done. At the bottom of the whole thing is the fact that the coarse aggregate and the fine aggregates are only filler material. As far as concrete is concerned, the paste is the only reactive part, and that is something which needs to be emphasized over and over again. The discussion will be on defining and understanding concrete properties, which we will try to build from our understanding of the properties of cement paste. Now, going back to this slide, which is more or less the same as what we used perhaps in the first few lectures, concrete needs to be evaluated from the point of view of performance, constructability and economy, and we need to have the basic selection criteria for concrete constituents and concreting operations, keeping these three things in mind. How do we want the concrete to perform in the fresh state or the hardened state, whether the concrete that we have can be used for the kind of construction process that we have in mind, and at the end of it, is the whole operation going to be economical? Now, from that point of view, if we examine performance, performance can be viewed in terms of strength and let's say durability. Strength is the ability to resist load, and in the case of concrete, most of the time when we talk of strength, we are talking of compressive strength. Even though we have situations where we are interested in tensile strength or flexural strength, most of the time we are concerned with the compressive strength, and the designers are concerned with the characteristic compressive strength, and those details we've already covered to some extent in this course, and we will also come back to them later on. Then performance can be in terms of the durability of the concrete, which is basically the ability of the material to provide tightness to prevent ingress of foreign agents or those that can cause deterioration to the concrete matrix. Now, when it comes to constructability, the ease with which the construction can be carried out, we have to see the workability of the concrete, that is the ease with which it can be worked in fresh state to different shapes and sizes without segregating. that is without the coarse aggregate being separated from mortar, without the paste being separated from the sand, and without the water appearing on the top as if the other materials have been allowed to settle down. Then there are environmental conditions that are important to consider when we are talking about constructability, and these could be in terms of exposure conditions of the structure or the conditions during placing. For example, we have situations where the temperature is very high or it is very low. So we need to put in place conditions or specifications for hot weather concreting or cold weather concreting. Sometimes we are trying to place the concrete under water. So that's a very challenging situation, and we need to design our concrete accordingly. Coming to the method of construction, we have shotcreting, where the concrete is just shot, it is gunnited, it is placed under pressure using a gun on a surface, and in those kind of cases the kind of properties that we need as far as the concrete is concerned are quite different from that of normal concrete. Similarly, if we are using tremies to place concrete under water, the kind of properties that we are looking for are quite different. So we can relate any of these things here to finally the performance that we want. And lastly, there is the economy. There is the aspect of not making the concrete construction too expensive. That can be achieved by talking about materials, whether it is cement or it's water or it's aggregates or it is the chemical admixtures or mineral admixtures which are involved and so on. Economy can also be in terms of time, how much time it takes or it will take to complete a structure. Sometimes the time available to us is very small. This is, for example, true when we talk about repair work. We cannot close a bridge for too long. In that case, we have a limited time to complete the operation, and therefore time is of essence. Similarly, there is the funds available to us. What is the kind of funds available to be able to complete a project? So these are the kind of things, an interplay between constructability, economy and performance. That is what is the challenge to an engineer, to come up with the right kind of concrete. As far as the constituents are concerned, normally we talk of concrete made up of cement, water, fine aggregates and coarse aggregates. We talk in terms of mortar, coarse aggregate and the interface, and we talk in terms of filler, that is the fine and coarse aggregates, and the binder, which is the water and cement. This here is a comparative picture of what normal concrete, which is called the regular mix here, looks like. If we say that okay, 45% of it is coarse aggregate, 25% is fine aggregate, and about 28% is the volume of paste. Now for a special purpose, for example in the case of self-compacting concrete, the coarse aggregate fraction instead of 45% comes down to about 36%, and the sand remaining the same, this kind of 8% of additional fines are added, so the total mortar content increases. So these are the kind of adjustments that we make when we go for the design of special concretes. This is just a reiteration of the previous figure. Cement by volume ranges from 7 to 15%, water about 14 to 21, sand is about 24 to 30, coarse aggregate is 31 to 50, and air varies from about 0.5% to 6%, and concrete generally has about 25% of paste, 50% of mortar, and about 40 to 50% of coarse aggregate. Now this is the concrete that we deal with. This is a slice of hardened concrete, and it can be seen that it is made up of coarse aggregate with, this is a slice of hardened concrete which is modeled as aggregates, whether they are fine or coarse, suspended in a cement matrix which has hardened cement paste, the solids, and some voids within the paste. Now from this slide we get into models, where we say that okay, if there are aggregates suspended in paste, they can be placed like this, that is, these are the aggregates and this is the paste. So the aggregates are all here, the paste is here, and this is the phases are in series. And similarly we can talk in terms of a situation where the aggregate phase and the paste phase is placed in parallel. Now the series and parallel comes from the fact that if we apply a load like this in these cases, this is what is the parallel part of it and this is the series. So as the load transfer mechanism is different, in this case, since the force is being applied on a certain area, the stresses in the two phases will be the same, the strains or the deformation will be different, whereas in this case the deformation in the two phases will be the same and the stresses they carry or the forces they carry will be different. So this is the difference between the series and the parallel configuration as far as concretes are concerned. And obviously in real life concrete, neither the aggregates are in series nor they are in parallel, but some kind of a combination. What we need to understand and appreciate is that a model of concrete or our understanding of concrete has to be that yes, it is a material which is a composite where one phase and the other phase are different, and at the end they also have an interface. This interface is the so called ITZ, and this is how the interface appears in the two configurations that we saw. So this is a zone surrounding the aggregate particles in concrete and is commonly referred to as the ITZ, which in a diagrammatic form, the way we have represented this picture here, will become something like this. Now if we look at concrete as a three-phase system, we have the coarse aggregate, the mortar and the interface. We can also look at it as aggregate, cement paste and the interface. Now when the two phases, which is the mortar and the coarse aggregate, or paste and the aggregate, they are held in series, and when they are held in parallel, the importance of this interface is obviously different. So when the load is applied the way it is shown here versus the load is applied when it is shown here, in this case the role of the interface is quite different from the role of the interface here, and that is something which we must keep in mind when we model our concrete or when we understand the bulk properties of concrete. Now how does this interface form? This interface is formed because of bleeding. That is one of the reasons for forming this interface. Bleeding is the separation of water from the other constituents. We must remember that as far as concrete is concerned, all the constituent materials, sand, coarse aggregate and cement, they are all heavier than water, and therefore they tend to settle down when they are mixed with water. In other words, water appears at the top, and that is the bleeding that we talk about. We have discussed this in our initial discussion, and you may go back to that discussion and understand the situation a little better. Now, having said all this, finally we have concrete as a composite, and its properties can be seen in terms of the properties of the constituents and their interface. So what we will be looking at in the subsequent lectures is the properties of concrete, that is workability in the fresh state, and in the hardened state we will be talking about permeability, strength and the stress strain curve. So this set of properties is what we will be talking about, building from our understanding of cement paste. We have understood or we have worked about cement paste, the hydration and the hydration products and so on. We will now graduate to understand the workability of concrete, the permeability of concrete, the strength and the stress strain curve of concrete from that understanding, and the fact that the paste is an important part, but yet it is only about 25% as far as the volume is concerned. So when we talk about the bulk properties of concrete, whether it is permeability or strength, or it's the stress strain curve, or the workability for that matter, we will keep the properties of the ingredient. So for example, when it comes to workability, the properties of the coarse aggregate are also very important to keep in mind. So we've already studied the properties of coarse aggregates, and it's now only a matter of applying that understanding to the properties of concrete. So now this is our work plan for the next few lectures. Now before we move on to that, I would like to take time today to talk a little bit also about the classification of cements. Here we show the ASTM C150 classification of cements, which is prescriptive based specification, and we can see that cements have been divided into 6 types of cement: type 1, type 2, type 2 MH, type 3 and type 4 and type 5. Whereas type 1 is a general purpose cement which is used when special properties specified for any other type are not required. Type 2 cements are moderate sulfate resisting cements. Type 2 MH are those which are moderate heat of hydration and moderate sulfate resistant cements. Type 3 are high early strength cements. Type 4 are low heat of hydration cements, and type 5 are high sulfate resistant cements. Now, how are these cements different from each other? That's one question. And can there be another system for classification of cements is the other question. Now taking up the second question first, ASTM C1157 classifies cements based on performance, and that is type GU, type HE, HS, MH and LH with the description which is given here. So the general purpose cement is when no special properties are required. HE is high early strength cement, HS is high sulfate resistant cement, MH is moderate heat of hydration, and LH is the low heat of hydration. So now, what are the properties of cement that need to be borne in mind when we are trying to classify the cements? So if we look at this table here, for example, there is a compound composition and the physical properties of cement for the different types. So type 1, 2, 3, 4 and 5. If we look at this table, so we use type 1 cement, which is the general purpose cement, as a basis for discussion. So now if we look at, for example, type 3 cement, which is the high early strength cement, there is virtually no difference between C3S, C2S, C3A and the C4AF content, but the plane fineness is 550 square meters per kg, whereas in the other cases it's about 365, 375, 340 and 380. So basically what has been done is that it is nothing but type 1 cement or a general purpose cement which is ground much finer. So increasing the fineness of cement makes more surface area available for hydration and therefore has high early strength development. So as far as the specifications are concerned, we can say that, well, unless the cement has a certain fineness, it will not be classified or it will not be called a high early strength cement. So fineness is a parameter which we use in this case. We must also see that as we increase the fineness, the heat of hydration is also increased. So these are the kind of things that we would like to keep in mind. Similarly, if you look at type 4 and type 5, the C3A content is lower than what we have here in type 1. Similarly, when it comes to the heat of hydration, in the case of type 4, which is a low heat of hydration cement, we are talking of 235. Now how this 235 is achieved is by reducing the C3S and the C3A and increasing the C2S content. So, it is the early stage of hydration we want to control the amount of heat that is liberated, and that is why we have specifications on the 7 days heat of hydration in terms of joules per gram as 235, which is the lowest among all of them and is much lower compared to the type 1 cement. So, this slide here is basically an illustrative example to have you think about the different classifications and also the properties of cement. Coming to the Indian standards from the same point of view, one basis for classifying the cement in India is compressive strength, and in the fourth lecture we have talked about grade 33, 43 and 53 cements, and other than that we also have rapid hardening cement or the sulfate resisting cement, the low heat cement and the super sulfated cement. Now, if we look at these cements, here we have a similar comparative statement or a table which compares the physical requirements for the rapid hardening or the sulfate resisting or the super sulfated and the low heat cements. So, now here if we look at our numbers, when it comes to low heat cement, we are talking of 272 or 314 kilocalories per kg of the heat of hydration at 7 and 28 days. It is only in this case in India that a certain number has been laid down. Similarly, for the minimum compressive strength for the rapid hardening cements, the number is much higher compared to the others. I would also like to draw your attention to the fact that in the case of low heat cement, the initial setting time requirement is not 30 as it is in the other cases, but it is 60, which means that we expect the low heat cement, we are prepared for the fact that the low heat cements will hydrate more slowly to begin with. So, what we have done today is to prepare the groundwork to transit from the properties of cement paste and a discussion of hydration reactions and so on to the properties of concrete in terms of strength, durability, permeability, the stress strain curve and so on. We have also spent some time trying to put the classification of cements together in light of the properties of cement that we are familiar with. Thank you.